Properties of Bezier curve. Uh, like what is really a speciality of this curve? Why this curve is given so much importance is one of the subjects of study now. This is what is shown here is a cubic Bezier curve where it is defined by 4 control points, that is P0, P1, P2 and P3. One should remember here is that each P0, P1 which are shown here is a vector consisting of 3 components x0, y0, z0 or x1, y1, z1. Now the tangents at the endpoints are defined by endpoints and their adjacent points. So these are the endpoints. If I look at what are the tangents at these endpoints, they are defined by the last 2 points. For example, even if I take, let us say, a Bezier curve which has 6 control points, then I am defining a quintic Bezier curve. If I take, let us say, what is the tangent? Tangent is always follow the direction where you are going from point. If I join them by a straight line, so I have a vector which is going from P0 to P1, which will always represent the direction of the curve. So this straight line will always be a tangent to the curve, is one of them. So it interpolates the last points. Then the slopes which are first derivative are defined by endpoints and one point which is next to that. So same is true with here, like the slope in the case of endpoint is defined by P2 and P3, which are in this case. Now this property is not restricted to what is called as endpoints or the slopes. It can be extended to higher also. That means if I want to know the second derivative of the curve at the endpoints, they are completely defined by the last 3 endpoints. Like if I take P0, P1, P2 will completely define what is the second derivative, or more commonly what you call as a curvature. So curvature is defined by that. So if I look at expressions for curvature, these are the kappa which is shown here, kappa 0 and kappa 1 are the curvature of the curve at the endpoints. So what do you mean by curvature? Curvature is nothing but 1 by the radius of curvature. So the local radius of curvature, when I take a reciprocal, I get a curvature. So the curvature at 0 and 1, that means this is not at point 1, this is the end point, that is when u is equal to 1, this is when u is equal to 0. I have an expression which is given for the Bezier curve which has been derived. If you really look at this, what are the points on which k0 depends is it depends on P0, it depends on P1 and it depends on P2. Now this expression is not necessarily for cubic curve. This expression for curvature is a very generic, whether I am using a quartic or a quintic, or let us say I am using 10 points to define a Bezier curve, still this is the expression which is used for curvature. And similarly the curvature at the other end point is completely defined by 3 points. What are those points? It's Pn, which is the last point, then you have Pn minus 1, one prior to that, and Pn minus 2, that is the second one which is prior to that. This means, suppose if I take, let us say, n is equal to 10, that means I have 11 points which goes from 0, 1, 2 up to, let us say, 10. Whatever may be the position of, let us say, the points, for example, P0, P1 and P2 will affect whatever may be the, let us say, the coordinates of P3, P4, P5 etc. intermediate, that does not affect the curvature value of the curve. So it is only defined by the 3 points. So we can say that a second derivative will be defined by the 3 adjacent points, slope will be defined by 2 adjacent points. If I go one level lower, that is curve passes through the last points, and same thing can be extended to higher. Like if I take the third derivative, this is the second derivative, if I take the third derivative, that will be defined by the 4 points which are starting from end point and the neighboring points. So this property is one of the unique properties of Bezier curve which we have seen. So we have seen basically for the slopes and the curvature, but the same thing can be extended to higher orders when it comes to the definition of the curve. Here is another very interesting property of Bezier curve, is that, as we said, sequence of points is important in order to define the Bezier curve, but if I reverse the sequence, I get back the same curve. Like, suppose instead of giving P0, P1, P2, P3 as input, I give, let us say, input as P3, P2, P1 and P0. That means you are keeping the order same but only reversing it. And if I try to plot the curve, or try to come up with, let us say, mathematical definition for the curve, you have the same curve. That means curve does not change its shape or size by reversing the order of points. Okay. But if I change it other way around, then I may have a difference. That means one can say that the curve is symmetric about the two functions, that is 1 minus u and u. Only thing which you are trying to do is reversing. You are starting with, let us say, u cube term and going to 1 minus u cube, whereas in the other case it is different. So, if I just reverse the points, okay, this is the case where I am starting from P0, P1, P2 and P3, it is the same curve, but only thing which changes is the direction of parameterization. Like, whenever you define a curve, you also specify a parameter range, that is, it goes from 0 to 1, u is a range. So, now u is equal to 0 corresponds to a different point, and when I say u is equal to 0.3, it will be different for the two different curves, but the curves are the same, only the direction of parameterization has changed in this particular case. So, reversibility of the curve is important. Now, why is this important is, suppose you are given a set of points and you have to define a curve, like instead of, let us say, reading from one direction, if I have to read from the other direction, or the way I collected the data points may have reversed. So, it should not change the shape of a curve, I should still get the unique curve in the case of this. So, this is another very interesting property of the Bezier curve which is shown here. The other important property is that the curve is invariant under affine transformation. Now, I think this needs some explanation. Like, usually what happens in geometric modeling, or that is CAD and computer graphics work, is that suppose if I have to define a curve, let us say, which is located somewhere in the space, you first try to define the curve at some convenient location, let us say either in a xy plane, or let us say, or curve starting at origin, and then you place this particular curve wherever it is intended to be. So, in order to do that, you do a transformation. These are called as the geometric transformation. So, the common transformations which are used, geometric transformations, is one is translation, that is, you move a curve from one place in a space to another place in a space. So, a transformation can be defined by defining a vector which is a translation vector, which is translation in x direction, y direction and z direction. Similarly, I can have a rotation transformation. Rotation transformation could be either rotation about x axis, y axis, z axis, or any axis, any arbitrary axis which is defined in a space, and or I can have a transformation like scaling. When you are scaling an object in x, y and z direction, either the scaling factors in x, y and z directions can be same or they can be different. Then there is also operations like transformation operations like shearing, which is also one of the very common operations. So, these are four common transformations which are used, that is translation, rotation, the scaling and shearing. The only difference is the translation and rotation transformations are called as a rigid transformations. It will not change the shape of the curve, it will only change the location, that is where it is located and position, whereas scaling and shearing transformations changes the shape of the curve. Okay. Like when I scale an object, for example, some of its properties changes. What is the length of the curve? It will be a different when I scale an object with certain scaling factor. Now, all these 4 transformations which are applied to Bezier curve are invariant. What do you mean by invariant is, like if I apply the transformation to the control points, okay, I will get back the same curve, which is nothing but as if you are applying the transformation to the curve itself. This can be demonstrated by a simple example. Suppose I have, let us say, a curve here which is defined by 4, a cubic Bezier curve which is defined by 4 control points. Now I move all the control points, let us say along certain directions. So you have a vector where P3 has been moved to a new position which is called as a Q3, P2 is moved by Q2, so P1 is moved to Q1 and P0 is moved to Q0. So if I draw a vectors, these are all the same vectors. So there is a rigid translation which has been done. Now the question is whether I should first, like if I want to, let us say, translate the curve, should I first define the curve and translate, or translate the control points and define the curve again? These are the two situations. One situation is, like first I have defined the curve with P, P0, P1, P2, P3 as control points and apply transformation on the definition of the, that is whatever is the mathematical definition which is given to Bezier curve, so that I get back this. Another this thing is, if I, since these control points are used, first you transform the control points and then use the new control points to define the again Bezier curve. Both are one and the same. Okay, that is why you say that the curve is invariant under transformation. Same thing is true with rotation and other transformations also. This is actually a very important property. Otherwise, if this property is not there, then there are definitions for curves which are not invariant. In those situations, you have to also define whether your transformation is applied to a curve or to a control points or to the input which is defined, which is like a very difficult thing to handle. So very convenient thing to do is to use like Bezier curve which are invariant this thing. Same thing can be demonstrated for rotation, scaling, and also for operations like shearing operations which are used about that. There is another property of Bezier curve which makes it really appealing, is what is called as a convex hull property. Okay. You may have come across the term convex hull. Okay. What is a convex hull? Like convex hull is usually used to define, for example, often used with polygons. Okay. Suppose if I have let us say a set of points, or let us say a set of vertices, if I can find out, let us say, a minimum size polygon which can enclose all these points, then you call it as a convex hull. Okay. And it should be a convex polygon. You are also familiar with what is a convex polygon and a non-convex polygon. Okay. A convex polygon is one in which if join any two vertices of the polygon, the line joining these two vertices lies completely inside the polygon. Okay. This line completely lies inside a polygon. If it does not, then you have a non-convex polygon. So a convex hull is, suppose if I have a non-convex polygon, then you are trying to define a polygon which is like a convex hull of that. That means the minimum size polygon which encloses all the points and also convex in nature. Now this, I think convex hull property here is slightly different, in the sense what you are trying to do is, I have 4 control points and I can join them in a sequence 0 to 1, 1 to 2, 2 to 3 and 3 again back to 1. So there will be a polygon which is formed, which we know is called as a characteristic polygon or a control polygon. The curve always lies entirely inside the polygon. So it never goes out of the polygon, whatever may be the polygon which I am trying to use. So I will always have this property which is satisfied by the Bezier curve. Now I think this may not be a clearly evident. Suppose if I take an example, suppose if I change the, let us say, order of points slightly different. Suppose this is my first point which I am trying to use, then I take this as my second point and come back to this as third and fourth. Then you have a totally different curve which is coming, which is still lies inside a polygon. I think I can show you an example. Here is an example which demonstrates the convex hull property. So what is done in this Bezier curve? Bezier curve is shown in yellow here. This is the first point, this is the second point, this is the third point, and you have a fourth point which is shown here. Now curve has a tangent which is from 0 to 1. So the curve, this is the tangent which is shown. Similarly, it has tangential to last and last but 1. So this is the final curve. What is the polygon here? Polygon here is an intersecting, has an intersecting vertices. So it goes from P0 to P1, P1 to P2, P2 to P3. And if you see the curve, this polygon is in two portion, curve is also in two portion, and one portion lies entirely inside this triangle, other portion lies entirely inside this triangle. So the convex hull property is still met even when you have a control polygon or a characteristic polygon where you have intersecting edges. This is true for not necessarily for a cubic Bezier curve. This is true for higher order curves, irrespective of any number of control points which I take, and irrespective of any number of intersections which are happening. Like I may have a series of points like which are intersecting multiple times, still you will see that the curve always lies inside this particular thing. Now this is also this property can be used in number of ways. Okay, like how is this property helpful? Is first thing is, if there is a curve, you can always set the bounds. That means if I join the control points and come up with a control polygon, you know that the curve always lies and it does not go outside this. So you are in a way finding a bound for the curve is one thing. Second thing which you are also trying to use is since like it lies inside this particular bound characteristic polygon. Suppose if I want to find out, let us say, intersection of this curve with, let us say, another curve or a polygon or something, okay, or I want to find out, let us say, whether two Bezier curves are intersecting or not, let us say two planar Bezier curve. What do you do? Like how do I evaluate this particular aspect? Is since both of them are cubic in equation, if I write down the mathematical equation for curve 1 which is cubic, I have a second one which is also cubic, and if I try to solve, this is mathematically, it poses certain difficulties. Okay, you have to this is usually done numerically and you have also problems, but I can have a quick check. First find out whether the characteristic polygons are intersecting or not. Suppose if the polygons are not intersecting, you really do not have to go and find out whether the curves are intersecting. So a lot of computation can be saved in many situations, like finding the intersections, etc., which is usually done as a part of this. So convex hull property is used in number of ways in situations like this to find out, or basically to find out the intersections, or to define the curve, or to find a bounds for the curve, is basically one of the important properties which Bezier curve has. The another a very interesting property of the curve is what is called as a partition of unity property. Like we have seen that in the case of cubic curve is defined by 4 points. Okay, like there is x0, x1, x2 and x3. There is some weightage which is given to x0, x1, x2, x3 in terms of an expression. For example, if I take 3, n is equal to 3, I have this is 3c0 which is 1, 1 minus u to the power of cube and u to the power of 0, that is my first term. So I have this. If I remove the x0s, x0, x1, x2 and x3, okay, and just add the remaining portion, that means the value which is attached, or the, you can say, the value with which x0, x1, x2, x3 are multiplied, and add them, it is always unity. this always unity. That means whatever may be the u value, whether u is equal to 0 or u is equal to 0.2 or 0.5 or 0.8 or 1, whatever may be the u value, if I just add the magnitude with which the x0, x1, x2, x3 are multiplied, it always turns out to be unity. I think this is shown here by a simple example. For example, if I take cubic curve n is equal to 3, so this expression when you expand, it becomes 1 minus u cube, which we have seen. 3 is the binomial coefficient, the next one. Then you have 1 minus u square into u, then 3 1 minus u into u square plus u cube. So now whatever is the u value which I substitute, you always get back the value which is 1. Let us just check. For example, if I put u is equal to 0, what happens? So you have, if u is equal to 0, all of them will be 0 and this will be 1. If I put u is equal to 1, this, all these things will be 0 and I have still as a 1. Now let me choose, let us say u is equal to 0.6, just to show this. So I have 1 minus u cube, so 1 minus u cube would be 1 minus 0.6, which is 0.4 into cube, which is shown here, plus you have a 3, this is 1 minus u square, and into u, which is shown here, plus 3, which is a binomial coefficient, multiplied by 1 minus u into u square, which is shown here, plus u cube, which is nothing but cube of 0.6, which is u is equal to 0.6. Now if I add all these terms, that is the 4 terms which are coming, that will be value which is equal to 1. So this property is usually called as partition of unity property. This is true for other